Okay, when we're doing big O, we're often actually going to end up with something with big O of log base 2 of n or n times log base 2 of n. That's going to be super common. So far we've just looked at n squared, n times m, n plus m, but we're soon going to start looking at when the big O runtime includes a log. And just like addition is the inverse of subtraction and multiplication is the inverse of division, here exponentiation is the inverse of logarithmic. And I want you to just guess for that really big number there, what is log base 2 of that number? And then using the equation on the left with y equals b to the x, or the equivalent x is equal to log base b of y, we're asking the questions, how many times can I divide y by b before I get to 1? And the answer is x. And the answer there on the bottom, the answer is 39. That is tiny. I think a lot of times people see the graph for log and they think square root. But like, yo, 39. So on the previous slide, we were just looking at the expression with variables. But I think looking at that same information, saying, oh, 2 to the third is 8, or log base 2 of 8 is 3. I think if your instinct is ever, oh, I don't really get logs, just be like, oh, but I get exponents. Exponents are no big deal. And this is just a rewriting of exponents. Now, I don't feel like it's a particularly natural rewriting of exponents, but the key thing is that our understanding of log is going to rely on our understanding of exponents. And you've got that. So when we're doing log base 2, that's the power you have to raise 2 by in order to get to x. So there are some common ones where they're just the powers of 2 that you already know, like 2 squared, 2 to the third power, etc. And we can look at these bigger ones. And the thing I want you to really take away from this and that example on the first slide was that log base 2 of x is really small. There can be a really, really, really big x, and we're still going to get a super small log base 2 of x. Now we're going to look at how log base 2 of x, or log base 2 of n, is going to apply to reasoning about the big O runtime of trees. And because binary search trees never got rearranged, we could end up with super lopsided trees or super balanced. Let's look at the case of the super balanced case. So here we have balanced binary search trees. So for every node, it's 2 sub-trees, or it's 2 children. Those subtrees are the exact same size. And I want you to fill in the blanks for the trees that I have on the right. I've listed the number of nodes, and I want you to identify the number of leaves, and then the relationship between the nodes and the leaves. And I'll pause here. That's wrong. You should pause here. I'm going to keep going. I'm sorry. Okay, so if we look at it, there's almost twice as many nodes as there are leaves. It's actually the number of leaves times 2 minus 1. That's how many nodes we have. And if we write that in terms of the height, the number of nodes is equal to 2 to the height plus 1 minus 1. And you can check that for specific values if you want. So I want to use another example to give us intuition for the fact that the total number of nodes in a perfectly balanced binary search tree is just going to be the number of leaves times 2 minus 1. So imagine we're playing a tournament, and we have a power of 2 number of teams. That's on the left-hand side. So these leaves are our initial teams, and we're doing single elimination. So to get to the winner in the end, every team but one needs to lose once. So all these non-leaves are their games that they play, and in each game, one team loses and is removed from the tournament. This is just another way to look at exactly the same thing we saw on the previous slide, where the total number of nodes in one of these perfectly balanced binary search trees was just 2 times the number of leaves minus 1. So more than half, or 1 more than half, of the nodes are going to be in the leaves. And again, if every team besides the one champion loses exactly once, then that's x minus 1 games. And here we're using x as the number of leaves in the tree, and that's not a super common variable usage. But again, the total number of nodes is just x plus x minus 1, so 2x minus 1. Okay, so if the nodes that we have in a tree were 2 to the h plus 1 minus 1, and that h was our height, then the number of leaves in our tree is 2 to the h. And if we rewrite that leaves we can see that h is equal to log base 2 of the number of leaves. And so h is about equal to log base 2 of the number of nodes, because there's just about twice as many nodes. So if we have the number of leaves in the tree as x, we know that x is 2 to the h, and if we take the log of both sides, there's this log rule that you might not remember where when the term inside the log has an exponent, you can actually move that exponent out to the outside. And going back to the original slide, you might be able to prove that to yourself too. Okay, so if we apply that, we can move that h to the outside. So now log base 2 of x is equal to h times log base 2 of 2. Well, log base 2 of 2 is 1, because 2 to the 1 is equal to 2. So here we can see that the height is log base 2 of x, where x is the number of leaf nodes. Okay, we're going to try one more explanation to try and convince you that the height of a perfectly balanced binary search tree is about log base 2 of x, which is the number of leaves, or about the same as n. So here we're thinking about how many times can I divide the number of leaves x by 2 to get to 1? And you can think about that as the x is the number of leaves on the bottom, and then how many times do I have to divide them in half, or divide them by 2, so that's like the branches going up. And the number of those edges, that's our h. So in the tree shown on the top right, there's 3 edges from the top to the bottom. So to divide x leaves on the bottom in half, h times, we're going to get to 1. And again, just rewriting that exponent as a logarithm, we can see that the height is equal to log base 2 of x. So it's super common for us in computer science to talk about a balanced binary search tree as having a height of log base 2 of n, where n's the number of nodes. And since there's only twice as many nodes in total as there are leaves, then that height, maybe it's off by 1, but in big O, we don't really care about that. So we can ground our understanding in the number of leaves and say the height is log base 2 of the number of leaves, which is basically the same, or just half as many as the total number about half as many as the total number of nodes. Okay, the key takeaway I want you to have is that a balanced binary search tree is going to have a height of O of log base 2 of n, where n's the number of nodes in the tree. But actually, a binary search tree can actually have a height of O of n, because imagine you added the numbers to a binary search tree from 1 to n in exactly that order. Imagine what that tree would look like. That actually would have a height of O of n. And the height of the binary search tree is going to be important for us as we're thinking about traversing the tree. Maybe we have to go from the top down to the leaves. What's the big O runtime of that? Okay, these are our 2 key takeaways.